I still have 40 minutes, or do I do it 1.5x? I don't see anyone. OK, I'll do 40 minutes. Who knows? Just kidding. Let's do, this is my name, by the way, Andrea. That's my handle on the internet. I come from central Italy over there. I will skip the whole bit about their pineapple on pizza. Will I be killed? I hope so. All right. So I work at a company called Vips, which is a streaming platform for comedy shows and concerts and live music shows. And we have a subscription service that we recently signed up, recently released. And you can sign up on vips.com. It's very, very cool. The whole thing is built in Elixir, which is very cool. Lots of LiveView. It's like a very small team doing lots of stuff with Elixir, so very cool. I will not go into it because it's a whole other talk, but that's where I work. I've also been a member of the Elixir team for 7-ish years now, 7.5, and I've been using Elixir for a little bit longer than that, so it's been a long time. I don't really do anything for the Elixir team. In Elixir itself, I mostly do libraries at this point, but still I have the title until they kick me out. And I also wrote a book together with Jeffrey Matthias called Testing Elixir, which is about testing in Elixir. It's been out for quite a while now, so you can go check it. It's from Prague, so you can go check it out there. Also writing another book called Network Programming in Erlang and Elixir, which is going to be out eventually. So that's what I've been interested in lately, and that's what we're going to talk about today. The outline of the talk is that, first of all, I want to say something, which is that I don't think I can teach you very much in 30 minutes, 35 minutes. So the goal of a talk for me generally is to just expose you to concepts and just give you ideas and like spark curiosity so that you can go, tell you stuff that you might have not ever heard about or you might know the name of or, stuff like that. And then you can go properly learn after this because like in half an hour, I don't think I have the time to actually teach anything. So that's what we're going to do today. We're going to do a big whirlwind tour of the networking on the Beam, so the stuff that you can do and how it works and why it's a good fit, why the Beam is a good fit for networks. And we will start by talking a bit, why the Beam is such a good fit for networks. And this is my favorite part of the talk. It's not technical at all. I'm just going to hand wave and talk about abstract stuff. And then we'll talk a little bit about servers and clients, so patterns for sort of building servers on the Beam and why it's such a good platform for doing that, and do the same for clients, how to build clients and why it works very well. So that's the plan. Let's get started. The first part is why is the Beam such a great fit for networks? The analogy that I like to use, that I think I heard first from Joe Armstrong, and then I've heard many times from then, is that the things on the Beam work like things work in the real world. And the analogy is essentially that processes and messages between processes work sort of the same way people work. So the analogy starts with a process, which is, let's think of a process as a person, right? And first up, a person can only do one thing at a time, right? Like we have one conscious task at a time. Multitasking is not it's not really a thing. Like let's say that at one time you can do one conscious thing, one conscious cognitive task, and that's exactly like processes, right? A process can only be doing one thing at a time. It executes sequential code. It can't do two things at the same time. It can only do one instruction after the other, sort of like a person. Okay. Then each person works sequentially, but I'm like multiple people work concurrently, right? I'm up here chatting and talking and moving my hands, and you're down there listening, right? So we're doing two different things at the same time. This is really the same as processes, because processes do things sequentially in their own little world, but then multiple processes can be doing stuff at exactly the same time, especially if you're doing that stuff on multiple cores, right? So you're actually executing instructions at the exact same time. Then comes memory. So people have brains, and they have memory, and they have thoughts inside those brains, and they can't share those thoughts and those memories with anybody, right? So we don't have the technology yet, at least. So this is, we are, this is sort of the same as memory for processes, because in the Beam, memory cannot be shared by different processes, right? Each process has their its own memory, and the other process can't really see what a process is doing. They can't really access its memory, its data, sort of like us. One more thing about this is that our memories and thoughts are sort of immutable. This is stretching a little bit, but bear with me, because once you have a memory, that memory itself cannot be changed. Like, memories, like we tend to alter them, but in an ideal world, like something happened, we have a memory of it, that memory shouldn't change in the future, right? And thoughts are immutable too, because you have a constant stream of thoughts, but each thought, you can't change a thought that you already had, right? You can only have new thoughts that update that thought maybe, but you can't really change it. And all of this works exactly like memory works in processes, right? Because in a process's memory is immutable, completely immutable. The data cannot be changed, so you can never write over a little piece of memory inside a process. You can only write a new piece of memory that references older pieces of memory and then eventually clean up the stuff that you don't use. But you can never change existing memory, right? Which is sort of the same as us. And now we got the analogy of a process being sort of like a person, fairly good, but also communication is very, has a lot of similarities between processes and people. How do humans share information? Generally, if I have a thought or if I have a memory, how do I copy it over to your brain? Usually by speaking or any other form of communication, right? Where I have to communicate something to you, so I can speak, I can write, I can, whatever. But anyways, I have to communicate that information to you. And communicating information sort of creates other copies of that information. So it's imperfect in the real world, but let's pretend it's not. But the idea is that when I talk to you, I am copying the information that's in my memory, that's in my head, I'm copying it over to your head. And then you store it in your head, right? And then you store it there, and now it's yours, and I can't take it away anymore. Right? Now it's in your head, now it's your memory, and I can't touch it. And you might see where I'm going with this, this is exactly like message passing on the Beam, right? Because if a process A wants to get some data to process B, the only way it has to do that is by sending a message. And sending a message from one process to another just copies the memory, the data that you're sending in that message. It copies essentially that data from process A to process B. So it's exactly sort of what I'm doing right now, right? And if you want to push this analogy a little bit more, we can also sort of say that speaking is asynchronous and listening is synchronous, which is sort of what happens with sending and receiving messages in processes, right? Because when I'm speaking, I don't really know if you're listening, right? I just speak, and I throw my words out there, and then I hope that someone nods, and then I understand that that you have been listening, right? And that's an acknowledgement coming back to me. But listening instead, you can't listen if someone is not speaking, right? You have to sit there, and you're going to wait for someone to speak. So listening is blocking. You're blocked until someone speaks, and you can receive the information. And speaking instead is asynchronous, and I need acknowledgement. And this is exactly like sending messages between processes. When I send a message, I don't really know if the process got it or if it's going to get it. I'm sort of guaranteed that eventually it's going to get it in order, but that's all. If I want to know that a process got a message, I have to wait, and I have to get the message, like an acknowledgement back from that process, right? Which is exactly the same as I'm speaking, and I have to wait for someone to do this with their head, and then I understand that they actually, receive the information that I just said. So I really like this analogy. That's, I think, why I like Elixir and Erlang and the Beam so much, because it makes it very natural for me to reason about these systems, because they work sort of like the world works. The good news is that networks work exactly the same way as all of these, as what we just said. So if you think about it, networks of computers really follow the exact same analogy that I described. So you have independent computers, that would be the people, which are processes on the beam, and each of those lives on their own. They can't really share the memory. There is no shared memory networks, like, to be clear. And if you think about like a database, for example, that's not shared memory, that's just another computer in the network, right? So that has its own memory. So you don't really have any shared memory. And these machines can talk to each other and share information by sharing information over the network, which effectively copies information from one machine to the other. It's not like you send the data from one machine, you lose the data, because you send it away. You just copy the data and send it to another machine. You have acknowledgements. You have asynchronous sending. You have acknowledgements for receiving data. So it's really, really very, very similar. And the similarities between the beam process architecture and the beam message passing and computer networks is even stronger than the one with people because, for example, if you focus on TCP especially, right? We're going to talk about in a second, but in that case, message semantics are exactly the same in that you're guaranteed that when you send a message, it's going to arrive and it's going to arrive in order. In the order that you sent it to the destination is exactly like messages on the beam. If a process sends multiple messages to another process, you're guaranteed that they're going to arrive and in the order that you sent them. And you can't get a situation where one message doesn't arrive and then the next one does, which is exactly the same as TCP. And so I think that's why network programming on the beam is so smooth. It works so well because like the constructs that you use to program systems on the beam is exactly like you have to think about stuff that then you have to think about when you do networks. It's the same problems. You're thinking about the same problems and the same patterns. And that's why I think it works so well, right? So the whole language environment on the beam has primitives like sending, receiving, all this stuff that really match the ones that you can find usually in networks, and especially in TCP, right? So for example, if you take a gen server as a process and you take a socket, which we're going to talk about in a second, the process and the socket are really good matchup because the primitives that the system gives you, like message passing and linking, they come into play really well here, right? So if data comes to a socket, it gets delivered to the gen server process here as a message. If the socket is linked to the gen server, so that if the gen server goes down, then the socket is cleaned up, and you don't have to take care of that by yourself. And this is really cool because like these are like linking, message passing. This stuff are primitives that are built into. They're not even OTP. They're just like the beam, right? They're built into the language itself. They're primitives of the language itself in Erlang and in Elixir. Cool. So the analogy is over. This is why I think this is my pitch for why I think it works so well. Networking on the beam works so well. And let's move on and talk about writing servers on the beam and like patterns for doing that. And then we will do the same for clients. We will do a very short recap of network programming first, so that we have an idea what we're talking about. So TCP is the most common protocol out there. That's what we're going to focus on the most. It's the thing that powers, HTTP and like most connections to like databases and message queues. Usually it's all TCP. The reason is that it gives you a bunch of guarantees that it's really hard to do stuff without. And we will not really talk about anything SSL related because it's just TCP but with encryption. So it doesn't really make any difference at the network layer. For TCP, which is a protocol, again, it's a network protocol. It's a way of for computers to agree on how to send data to each other over a network. TCP is a bidirectional protocol, so it's a protocol where servers and clients can communicate with each other, right? And the connection between a client and a server is persistent. This is one of the nice properties of TCP compared to other things like UDP, which is another network protocol where connections are not persistent. And as I mentioned earlier, the data is guaranteed to be sent and guaranteed to arrive in the same order that it was sent in. And then the center of TCP, there is the socket. And a socket is usually, it's like an operating system abstraction over all this lower level network stuff. And it represents the state of the connection, of the TCP connection on both sides, so on the server and on the client. The only difference really in a socket between a server and a client is that a client can create a socket and can connect to a server and not vice versa. So there has to be a server listening for connections for a client to connect. So the initial sort of handshake, the initial creation of the socket has to happen on the client connecting to the server. But then after that, the sockets are really the same, server side and client side. Behaves really mostly the same. So Erlang ships in the standard library with a module for dealing with TCP, which is called GenTCP. It does everything you need for doing TCP level stuff. It's an interface over operating system primitives, so like for doing networking, but it provides an Erlang API over that. So how do we do a server with GenTCP? It's really easy, actually. It's just a couple of function calls. So you call this function called gentcp.listen, and you give it a port. And a port is just a way that you identify, you know what a port is, but it's just a way that, to identify, to route connections to the right part of your computer instead of just to your computer. So to this program listening. And when you call gentcp.listen, it gives you back a listen socket. So listen socket is a slightly different thing than a socket. And a listen socket is the generic socket that just tells you that there's a server listening on the port. If you would then want to accept connections, so if you want clients to connect to this port 4000 here, then you have to call gentcp.accept on that listen socket. And then when the value that gentcp.accept returns is a socket that we were talking about before. So it's a TCP server-side socket that you can use to communicate with the client. And that's it. Then you have a socket. The server can communicate with the client, can send data through that socket. They can receive data through that socket. So that's really all there is to building a server. Most of the interesting stuff in this landscape of writing servers is not how this works. It's about scaling this stuff up, right? Like, how do I turn this into an actual server that can handle, like, whatever, 2 million connections on a single machine and stuff like that. That's where the interesting parts of networking are. You're rarely going to have a server that accepts one connection, and that's all it needs to do. So let's get straight to talking about that. The most sort of naive approach that you have in Erlang that I think you can implement for building a TCP server, or generally actually other kinds of servers as well without protocols, but we're focusing on TCP here. But is something that we can call an accept loop. So your server it starts a connection. It starts listening on a port, which gentcp.listen that we just looked at. And then it goes into this accept loop. And the accept loop is calling gentcp accept again and again and again. And when a client connects and to the listen socket and a new socket is returned, then we can spawn a new process that handles the communication with the client, and the server can go back to the accept loop, right? So you get a client, you spawn a handler process, and then you keep accepting. Then you get a client, you spawn another handler process, and keep accepting. So this approach already shows, I think, how really good the Beam is at this. So the processes on the Beam, they are lightweight processes, right? You can create a lot of them on a single machine. Their footprint is very light. So already in other environments, to do something like this, you already have to start thinking about stuff like threads, for example. So you might have like accept sockets on different. You can have an accept socket, and you might have to handle clients in different threads, but you probably can't do one thread per client because maybe you can't have like tens or hundreds of thousands of threads in the same machine. So you have to share the handling of a client, of multiple clients in a single thread. So it's already really hard, right? And because you can't afford spawning a process on every, you can't afford spawning a process for every incoming connection, right? And then the other really awesome thing here is that processes are isolated on the Beam, right? So this is a huge deal in a case specific like this, because it means that a failure in one process doesn't really, that's handling one client, it doesn't really affect any other process or any other clients, right? And this leads to servers that are really easy to make resilient, like they're resilient just on their own, right? Because you don't really have a way to say, for example, if you have a thread that's handling 100 clients, and then you have a SAG fault in that thread, and the thread crashes, and everything goes down, you lose 100 clients. Here, that just can't happen, right? Because processes are isolated, and memory management is isolated too. So there is no global garbage collection, which is awesome, right? Because every process which is handling a client has its own garbage collection. So maybe if a client has a very long-lived connection with the server, it's going to eventually see garbage collection happen. It's going to see a little hiccup in the communication with the server because the server is doing garbage collection. But it's really unlikely that that garbage collection takes a long time because it's garbage collecting one process. So how much memory can one process have realistically, right? So it's going to likely see very small hiccups. Sometimes you don't even see them because the connection, for example, for HTTP servers, usually what happens is that the connection to the server happens, and then the server builds a request, it sends it back, and then it throws away the connection, like the process is gone. So you don't even see, like the requester client doesn't even see the garbage collection happen, right? So you don't have this global garbage collection pauses that you have in other languages. So I'm really saying good stuff about this approach. Why did I say that it's most naive? There are a couple of issues with this approach. The first one is that with this approach that we just showed, the first one is that you can have sort of a problem where you don't have an upper bound of on the number of clients that you can spawn. And yes, processes on the beam are really cheap, but they also are not infinite. They're not completely free, right? So you can't have a server where you, for example, can spawn 100 million connections, unlikely. So for stuff like that, my general recommendation of what I've seen used most of the time is it's a dynamic in Elixir would be dynamic supervisor, which is a supervisor can supervise just dynamic processes. You can just throw processes under it, and it has an option to configure a maximum number of children that you can spawn under the supervisor. So that way you are going to have an upper limit, and at some point when accepting clients, you're going to say, okay, spawn another process, and the dynamic supervisor is going to say, I can't, I reached the limit, and then you can not accept that connection yet. You have to wait for, for some other children to be cleaned up and to finish. So that's one of the things, and the way that you would use a dynamic supervisor is that you would just put it between the acceptor loop and spawning your client handling processes. So now you still have a server that still calls listen and then goes into this accept loop, but instead of just spawning children left and right from the accept loop, now you spawn them under this dynamic supervisor. And the dynamic supervisor supervises these handler processes, right? This is not about restarts, because once a process crashes and you lose the connection with the client, you can't restart it because you don't know where the client is. You have to have the client reconnect with you. It's only about sort of controlling the number of children that you can spawn. And then the other problem with this approach is that it's accepting connections because we only, in the previous sort of setup, we only have one process doing the accept loop, right? So the accept call can become the bottleneck of your server, right? Because you can have maybe, for example, 1,000 clients connect all at once, and then they all hit accept, and then the 1,000th client is going to take a while before it gets a socket there, right? The good news is that Erlang, a while ago, it was not there forever, but a while ago, they added support for calling GenTCP accept from multiple processes on the same listen socket. So you can have multiple processes calling accept at the same time concurrently, right? And this effectively creates what we usually call an acceptor pool. An acceptor pool is, the idea is that you have processes that are into this accept loop. So you have a process that is like calling GenTCP accept, then it gets a process, and then it gets a connection, from a client, and then it spawns a process to handle the client, maybe over inside a dynamic supervisor. And then it goes back to the accept loop. So this unit now is a process, and you can have multiple processes doing this stuff, right? So This, acceptor pool is what this is called usually, and this is how libraries are built generally, right? Like what you see. So this is the complete setup here, where you have the whole picture, where you would have like something like an application supervisor or like a server supervisor or something, and then you have a dynamic supervisor for handling the connection process. That's what you see on the left, and that's what we're talking about with the dynamic supervisor. And those are processes that are handling the communication with the client. And then you have, for example, like, I don't know, called the TCP supervisor there, which supervises a listener, which is just the process that creates the listen socket initially, and then a bunch of acceptors. So that the acceptor supervisor and the acceptor process is down there. They are the acceptor pool that I mentioned, right, where you have process just calling, and then spawning processes under the connection, the dynamic supervisor on the left here. This architecture is very common, or some variation of this architecture is very common. Usually you don't have to write something like this. So for example, Thousand Island, which is a TCP acceptor pool library for Elixir, it's built like that. Also the other ranch is built like this, which is what eventually powers Phoenix right now. So they're all built like this. So you don't usually have to go write this stuff, but this is how these things work, so this now you know. Yeah, so this is these all patterns are all provided for you by the Beam. The supervisors are there, the processes are there, spawning processes under a different supervisor. All this stuff is provided by the Beam. So this makes for very resilient and very scalable servers, because you can imagine if I just throw more CPUs, for example, then I can have more processes doing more stuff at the same time. So you're going to eventually, come into operating system limits, like, for example, spawning too many sockets, opening too many sockets. That's usually operating system limit, but on the Beam, you're rarely going to hit this in a server in production. You're going to rarely see that the Beam is the problem with like spawning too many processes, because you're going to run into problems with like shared resources like databases or sockets and stuff like that. So anyways, if you want to go check out Thousand Island, this is how I would build a TCP server myself. If I were writing something like a database, I would use this as the server to accept connections and like scale that up. Or ranch if you're in Erlang as well. So now let's talk about clients a little bit. This was the sort of server whirlwind tour. What does the client side look like? And as I said initially, once a connection gets established, the exchanging data from server to client or client to server is really, really similar. Like the socket is really the same. The thing that changes is that clients have different challenges than servers that we have to worry about, and we're going to talk about those and why Erlang and Elixir and the Beam are very good at handling those. The first one is reconnections. I just mentioned this earlier, that servers really never have to think about reconnections. So if your server and a client connects to you and the connection drops, too bad, right? Like you can't do anything about it. You can't reconnect to the client because the client is not listening for connections. You don't know where the client is. It's not another server, it's a client. So the job of reconnecting when a connection goes down is all put on the client, right? And this, if you're building a server, this is nice because this takes away a whole set of problems from the server, but then you have to worry about this on the client side. So this is one of the problems. The other problem on the client side is pooling. So on the server, usually, well, we already sort of talked about pooling, right? Like we talked about how you don't really scale up resources for a particular client. You scale up resources for the whole server, but then it falls on the client to say, for example, if I have an application that's connecting to a database, do I only want one connection? Probably not, because then I only have like one data stream coming and going from the database, right? Usually what I want is a pool of connections, so it's multiple connections. But that pool of connections is just a bunch of TCP clients connecting to the server. The server doesn't care about that. It doesn't care that like those 50 database connections, like the database doesn't care that those 50 database connections come from the same application. They're just like 50 database connection like any other of the database connection that it's handling, right? It's the client that has to worry. This is actually my pool of 50 connections, and I have to do all this sort of stuff to route request through the pool in the right way, and there's a whole thing about that. So we will talk about it in a second. Reconnections are pretty straightforward for clients. So the main challenge is sort of understanding when to reconnect. Usually the problems that you're facing there and the things you have to think about are trying to reconnect in a way that balances reconnecting quickly enough, but also not overloading the server. There are really two common scenarios, I think, when a connection breaks. One of them is a very temporary break, like when a connection breaks in a truly temporary, very short way. And this can happen, for example, if a server closes connections, right? If a server closes connections because its resources are full, it's closing connections to free resources. So if you reconnect right away, there's a chance that the server will accept it. Or for example, another example is the connection keep alive in HTTP, right? Where you say like, okay, this connection should be left alive for 10 seconds, but after those 10 seconds, if you reconnect right away, it's gonna work, it's gonna reconnect, right? And so for these kinds of disconnections, it's totally fine to just like when the connection breaks, you reconnect right away. Fine, it's probably gonna work. If that first reconnection doesn't work, then we're into another category of disconnections, which is disconnection that can last longer. So for example, if I trip on the cable in the server room and I disconnect the server, it's going to take me some time to like plug it back in, right? And those connections, the server is going to be unavailable for 10 seconds or something, right? In those 10 seconds, I don't want to try to keep connecting constantly because I'm going to take up resources on my machine. I'm going to potentially take up resources on the server if the server is online but can't accept connections. So there's a whole category of problems I can introduce if I try to just blindly reconnect all the time. So for those situations, you use something called the backoff. And the backoff is simply a time to wait before reconnecting. And you want to, so one of the easiest backoff strategies that you can use is just reconnect every 1 second or something. That really quickly causes something called the thundering herd problem, because essentially fault connections, like if I trip on the server cable and then all clients disconnect and then all clients try to reconnect after 1 second, then maybe the server is up after 1 second because I was very quick to replug it, but then you have like all the clients connecting at exactly the same time, and that can cause potential problems in the server accepting all the resources at the same time. It might not be, it might create very high peaks. To fix this, usually what you can introduce is a small random variation in the backoff. So randomized backoff, maybe you want to call it, but for example, you can use clients can use a backoff of 1 second plus or minus half a second. So some clients will connect after 0.7 seconds, some clients after 1.4 seconds, and you sort of spread the clients reconnecting over a longer period of time, and you kind of mitigate this thundering herd problem. The other backoff technique that you will commonly see used is exponential backoff, which means that it increases the backoff every time you try to reconnect by a factor, like 2 or 1.5 or whatever. And the idea behind this is that a connection that doesn't become available right away, it's like the more time it passes, the more unlikely it is that it becomes available, very quickly. So the idea is that I don't want to try to keep connecting very quickly. I just want to like try after 1 second, then 2 seconds, then 4 seconds. Then eventually I go up to like 30 seconds, and then I'm like, okay, I'm gonna just keep trying every 30 seconds because the chances that like the more it's unavailable, the slimmer the chances that you'll just hit it right at every 1 second. And you're gonna have to deal with the connection being down anyway, so you might just as well try less. This is what like a backoff that looks like this, where starts exponentially and then at some point it's capped so that it doesn't grow infinitely, is what DB connection uses, for example, which is the connection library that Ecto uses for Postgres, for MySQL, the database drivers. So this is what you're probably using if you have an application that's using Ecto. You're using something like this, likely randomized as well. So you have randomized exponential backoff, where you do exponential backoff plus or minus a little random factor, a little jitter. Why this is easy to do on the Beam? This is not particularly to the Beam, really. I think it's sort of like a more generic technique. It's not a really hard technique to implement. One thing that I like to use for these on clients is I generally tend to build clients with gen state machine behavior, gen state M. which I'm going to talk about in a second. But one of the features of this behavior is timeouts. GenStateM has really good support for timeouts, and it makes it really easy to build sort of like these timers that fire once you have to reconnect. So it's back-off timers. It makes it really easy to build those and to like do the exponential backoff, the randomized backoff. So I'm going to talk about the GenStateM in a second, but I think this is a really fantastic feature for backups. And then the other thing to talk about here is pooling. Pooling is a really big area. It's a really hard area. So I'm just going to do a very quick whirlwind tour. There are different sort of ways to do pooling on the beam. The most common approach is that you're going to have a process hold the socket, and then you communicate with the process, either to get the socket into your own process and then use it, and then give it back to that owner process, or to actually send data to use that owner process as a proxy. So you send data to the process, it sends it to the socket sends it to the owner process sends it to you. These are sort of the ways to build clients on the beam, more or less. So this approach where you get the socket and use it and then you put it back in is usually sort of called like a checkout client, where you check out the socket, you use it, you send data, you receive data, and then at some point you check it back in. This is what, more or less, this is what, so it works. It looks more or less like this, where the caller actually uses the socket by sending and receiving data with the server. This is what, and so to make this work, then you also have to introduce usually something like a caller queue, and a caller queue just being like a queue of callers that want to use the socket, and that's because you need this because usually, if someone wants to use the socket while it's busy, you need to tell them, wait a second, it's busy, I'm going to give it to you. The big connection, which is what Ecto uses, again, is this library. A lot of the complexity is just in this slide, essentially like queuing callers, making sure that like they don't wait in the queue too much, making sure that if errors happen, like can I deal with the rest of the queue, or like should I just throw away all the clients? So all this stuff. And the big connection in Ecto, so when you talk to Postgres through Ecto, you're actually using this kind of pool where the process that is executing the query takes the socket, and then it sends the data on the socket, receives the data, the response to the query on the socket, and then gives the pool the socket back. This is a good approach on the beam because it can be a good approach on the beam because it doesn't copy data all around. Like the process that's doing the query is actually the one that's sending the data to the server and that's receiving data from the server. So it's very cheap memory-wise. You don't copy the data that you have to send around, right? The other approach, so the other approach is where you send the data to the process that owns the query, the data socket, and then that process sends data back to the caller when it receives it from the socket. And that's the only advantage, is that takes advantage of multiplexing, which is a property of TCP, where sockets can send and receive data at the same, like on a TCP connection, data can be flowing in both directions at the same time. If you think about the pool, the type of pool that the B connection uses, this can't happen because a single client is going to check out the socket, he's going to send the query, so only one way. The server, the database, for example, is going to process it, and then it sends it back only one way. So the data is only flowing one direction at a time. It's, there's compromises, but like in other cases, you might want to have a client that takes advantage of this. And to do this, usually what you can do is you can have, you can use the socket owner as a proxy. So that is sending data, and in the meantime, it's also like the data is coming back to the socket as well. To do that, you need to have a way to identify requests, meaning that like requests have to have an ID because this proxy process needs to know when some data comes back and it decodes it needs to know like who do I give it back to. So that's the main difficulty. Now, so for some bonus content, I mentioned that I would talk about GenStateM, and the reason why I usually tend to build these TCP clients with GenStateM is that usually it's easy to model clients as state machines, because a client can either be online or offline. It can either be connected or not connected, plus potentially more states, but at least connected and disconnected, right? So usually you have a client that is, it starts in the disconnected state, then it connects, and it goes into the connected state, connection breaks, goes back into disconnected state. That's pretty straightforward. The good thing about this in JStateM is that you can use this stuff to handle things happening in the client differently based on the state. So for example, if someone tells the client, give me the socket, but the client is in a disconnected state, it's very easy to reply, I don't have a socket, I'm not connected right now. And vice versa with the connected state, right? So this, for example, is how Radix works, which is a client for Redis written in Elixir. It works exactly this way. So you have like a JStateM, which is connected or disconnected, and it can know whether when you ask to send data, it can tell you, I'm not connected, I'm not going to send it right now. Cool. So conclusion for all of this. Let's wrap it up. One of the things that I purposefully didn't mention about writing software for networking on the Beam is let it crash. Don't let it crash. It's a bad idea. Network errors, I don't like them being called errors because they are not errors. Like a connection that breaks is not an error state in a network. It's something that is going to happen, period. So you have like it's not an handle state. It's like if you put a number input on a browser and someone types a number that you don't like. It's just like it's not an error. It's just like you put an error, like a number field, you're gonna get all kinds of numbers. That's how it works. So that's exactly the same way. Let it crash as a philosophy, I think, only works for unexpected errors. So the philosophy of let it crash for me is more like if it crashes, you're gonna be fine. Like if it crashes, it's gonna be fine. Because if something, you have a bug and something crashes, it's not going to bring down the system. That's the idea with let it crash. Like let it crash meaning like you're fine if it crashes, but don't just let it crash because when you let it crash, then you have to deal with like terrible logging, for example, because something just crashed and like you don't have a good chance to report it. You don't have a good chance to tell a user that something crashed, right? Like there's a million things that you want to do when something, for example, when an error happens, especially for something that's not even an error, like a connection breaking. If you want to have a fun experience for, this sort of corroborates what I'm saying about let it crash, go look at RabbitMQ source code. I think there are people, maybe I shouldn't say this because the RabbitMQ Summit here, but they have something called Supervisor 2 in their code base, which is essentially because they decided that if a connection goes down, then the process that owns the connection should crash. And so when that happens, you don't want to reconnect right away, right? We talked about connections. But if the process crashes and it's under a supervisor, the supervisor is going to start it right away, right? So they wrote Supervisor 2, which is a supervisor that implements backups so that if a process crashes, it can restart it after a little bit, right? And that's just like, then it's not crashing. It's just something that you expect to happen and like that maybe you should handle in the process, right? So this is generally... let it crash and networks don't go hand to hand. Like it's gonna, like the nice thing about let it crash is that it's going to make sure that you don't, for example, leak resources. Like this is awesome because like if your process owns a socket and your process crashes, the socket is cleaned, right? So that's great for sort of building a resilient system where you don't have a memory leak. It's not great for the user because the user is not going to know that maybe it's not going to get like a good message saying like, oh, the socket is down, the connection is down, like retry. It's just going to see a crash. So let it crash, no. The other thing that's difficult in I think on the Beam for building networks is generally that there are distributed systems, right? So the hard thing is concurrency. And this applies to people as well, because if I think about 3 people, I can understand what everybody's doing. Like it's very easy to think about a group of 3 people in my head. A group of like 100 people, I can't think about it. It's just like there's too many people. And this is the same thing when you reason about a system with like hundreds and thousands of processes. It can be hard to reason about all of those. It's not specific to the Beam. It's not specific to networks. Like it's just a problem of concurrent and distributed systems. I do think that the Elixir and the Beam really give you the best tools to deal with these problems. So it's still a great choice, I think, because like you have primitives and you have like really good tools to sort of make it a little bit easier to deal with distributed systems, with concurrent systems, even if those are just hard problems by themselves. Like you can't do anything about it. And so if you think about it, the Beam was designed for this, 30 5 years ago or something. It was designed for exactly this, where you have networks originally designed for telephone networks, and it's just another distributed system on the network, right? So you just like different computers talking to each other. And the language was designed to solve this problem, so it's not a real surprise that it's a good fit to solve the problem, which is exactly the same that we have right now, which is multiple computers talking to each other over a network. Just want to leave you with some resources as well. The slides are going to be online, but these are really great things to take a look at. Well, 2 of them are mine, so but there are other also good resources in there. Fred Hebert writes really great stuff about networks and Erlang designing systems, and then just another few resources. There's going to be in the slides. So that's all.